All right, start video 2C, third video of Unit 2, Functions and Relations. Okay, so what is a function? We see them all the time in our math classes, our CS classes, our daily lives. And there is an official definition, which we'll cover now, and see lots of examples. So a function, it's still kind of a hard thing to define because there's so many different types of functions. It's hard to kind of distill that all down into a couple simple rules. But here we go. A function, call it f, is a rule along with two sets A and B, such that f assigns each element of A to exactly one element of B. And the sets A and B also have special names. So the starting set is called the domain, and the ending set is called the codomain. So this is denoted so when we have a function with a domain and a codomain, we write it like that with an arrow. This is not the logical implication arrow. This is just an arrow that shows f is taking things from A to B via some assigning rule, right? And A is called the domain. B is called the codomain. Okay. So let's see some examples. Some you've seen before and some you've seen before that you have been told are functions, and some you've seen before that you maybe haven't been told that they're functions. Okay. So f of x equals x squared. We see that function a lot, right? But we never specify a domain or a codomain or anything like that. And I'll write a few more actually. 1, 2. So y equals 1/2 x minus 3. Nice little parabola. Number 3, sine of x, that's also a function. So, and for all of these, typically I'll say, so you kind of, it's just without even specifying it, the domain and codomain are both all real numbers. Oops. The domain and codomain are the set of all real numbers. And it's denoted with a capital R with an extra line, just like the similar style as with the natural numbers and the integers. And so just for clarification, what are the real numbers? Any decimal, well, I should say anything that can be expressed as an infinite decimal. So for example, 1 is a real number. It's not an infinite decimal, but it's, 1.0000 repeating. It's all, it's all the natural numbers, it's all the integers, it's all the fractions, and then it's all the things that can't even be expressed as fractions, like the square root of 2 or pi or e, right? And, there are infinitely many, of course. Um, but just all of the regular numbers you know and love. So it's excluding the complex numbers. That's it. That's all the real numbers. Okay. And that's usually what we think of when we can plug in, what can we plug into these functions? Well, any number we want, any real number. Okay. Another example, though, would be, oops. So a function, I'll call it P, whose domain is the integers and whose codomain is either true or false. And what's the rule? Well, it's just that P of X is equal to the predicate X is at least 5. So it's a predicate. So here the input is an integer and the output is a binary true false. So like just some examples of what we could plug in, and I'll kind of, this is the domain, this is the codomain. So, some examples here, right? Like P of 17, that's equal to true, because that's at least 5. P of 5, also true. 5 is at least 5. But P of, like negative 100, that's false. Okay. And then something like P of pi, right, that's undefined. Because the domain, I mean, you could say, oh, well, pi is, 3.14, so it's less than or equal to 5, so it should just be false. But pi is not in the domain because the domain is only integers. If we had switched the domain to be real numbers, then that would have been fine. But so pi is not an integer. Pi is not in the domain. Another example would be, I'll state the domain first, and the codomain would be students in this class. And the codomain would be one of these letters. And then what does the function do? It assigns each student a final grade, right? Assign each student to their final grade. So that's an example of a function as well. And there's no limit to how many functions there are, right? I would say since a lot of you are in CS, right, when you see in programming, right, there are things called functions or they're called methods. And they are like functions. They're maybe it's a little different. Maybe not exactly this definition, but usually there's some sort of input, which is your list of parameters, like whatever you need for the function. And then the output would be the return value. Some have a null or void return value, so it's not quite, a function, but you can think of something like sorting a list. So the input would be a list, and then the output would be that list, but sorted. And you could think of it abstractly that way. Okay. So now I want to talk about ways that um, assignments, ways to assign things might not be functions. So it's important to recognize when we have a function and something that's may sound kind of functiony, but isn't actually a function. So say there are several ways assignments might not be functions. So one way is that an input has multiple outputs. And I shouldn't even use those words because only functions have inputs and outputs. So if you have one input, but it gives you multiple outputs, that's not a function. But so an example of something like that would be like domain would be all CSUSB students, and the codomain, codomain would be the all courses. And the rule would be to assign each student to their courses. So this, I mean, in a very limited small scope, might be a function if every student was only taking one class, but that's not usually the case. So, for example, like if a student, Genesis, maybe they're taking math 23, 72. They are. And maybe they're also taking, so I don't know, CSE 2010. Right? Here, their Genesis is being assigned to multiple things, so therefore it's not a function. Because for a function, remember, it assigns each element of A, so that would be the student, so that's okay, but to exactly one element of B. Well, they're in more than one course, so not a function. Another way that something might not be a function would be an input might not be well defined. Or I should say a rule might not be well defined. So an example would be like an algebraic function, f of x equals 1 over x. And I'll just say the domain and the codomain are both all real numbers. What's the problem here? Well, you can't plug in everything in the domain because you can't plug in 0. So f of 0 is undefined. And right, 0 is in the domain, so you should be able to plug it into the function. 0 is in the domain. So we should be able to plug it into F, right? But we can't. A couple of ways you could just fix this if you really need it to be a function. You could just take 0 out of the domain and say, okay, the domain is all real numbers except for 0. Or you could just say the domain is all positive real numbers, or then it'd be fine. Maybe an alternative that sounds more strange would be to add some new symbol to the codomain that 0 would go to. So you could say, okay, now I want to be able to plug in 0, and now my codomain is all real numbers plus this abstract thing I'm going to call infinity. And then I'm going to say that if I plug in 0 to this function, I'll get infinity. And that actually has some validity to it. That's a thing that mathematicians do sometimes. Even though 1/0 is not technically infinity, um, there are some similar behaviors. So that's sometimes what's done instead of just forgetting about 0. Okay, what's another problem that could arise, or another thing that could make something not a function? Let's see, can I fit this on the screen? Probably not. So an output might not be in the codomain. So an output might not be in the codomain. So something like if the domain is 2372 students, I should say math, 2372 students, and the codomain is 0 to 100, just the integers. And the rule is to assign each student to their final grade as a percentage. So what's the problem here? Well, at least in my experience, I've never had a class where everyone's final grade is a whole number percent. Usually there are decimals involved. So now what if a student gets, a 92.5%, right? There's no way to assign them to something in the codomain, right? 92.5 is not in the codomain. So that's another way. Some sort of relationship or assignment might not be a function. So we have all these 3 ways for relations to not be functions, but we still want like a general description of what these types of objects are, and so that's what we're going to do next. So we're going to talk about something called the Cartesian product, and then jump into what a general relation is that's more that encompasses more than just functions. Okay. So definition. The Cartesian product of 2 sets, A and B, which is denoted A. It looks like multiplication, it's the same symbol, but you don't really say A times B, you usually say A cross B. And it's the set of all ordered pairs. Whoops, ordered pairs AB, where A is an element of A, whoops, and B is an element of B. Okay, so let's just look at an example before we try and connect this back to functions. So an example would be like if we have the set A, that I'm just going to call A, B, C, and the set B, which I'm going to call 0 and 1, or just it's going to be those. So those are my two sets. And so A cross B is a completely new set. That's all of the ordered pairs. So I take an element from A and I take an element from B, and that gives me an ordered pair. So one of them is A0. Another one is A1. Another one is, so that's done with A. So now A in the first coordinate is what it's called. That's done with. So now I'll start with B. So B0 and then B1 and then C0 and C1. So this new set has 6 elements. They're completely different objects, right? In A, those are just letters. In B, those were just numbers. And now in A cross B, the elements are ordered pairs of things. And so another example that you are surely familiar with, but maybe haven't seen it like this, is the XY plane, also sometimes called, not coincidentally, the Cartesian plane or Cartesian coordinate system. The XY plane is a Cartesian product. What is the XY plane? It's, just this thing. Here's the X, here's the Y, infinite in both directions, or in all 2D directions. So the XY plane, which is just the set of ordered pairs XY, is just the real numbers cross the real numbers, right? So you could plug in, any X, any Y, and this is how you can start to see that functions and relations are related, or I should say functions and Cartesian products, because any function, well, any function in, from real numbers to real numbers, which are all the functions we are used to from algebra, pre-calculus, calculus, if you're taking calculus yet, you can graph them. And this is what graphing them is. You're just illustrating a Cartesian product where the X value is the input and the Y value is the output. So you can view any function as a Cartesian product where where A is the domain and B is the codomain, or maybe B is the set of outputs, and you could do that. So little mistake there in what I said, but I'll kind of relations is the more general thing we want to discuss. But I hope you see how they're kind of related. Okay. So what's a relation? A relation R is a subset of a Cartesian product. Where A is, called the domain, and B is called the codomain. Okay. So one example would be sorry, A equals, I'll just copy the example we had before, but we'll slap a relation on there. That's not what I had before. It was ABC. 0, 1. We know the Cartesian product. It was those 6 elements, these 6 elements. And so we can just take any subset of that and call that a relation. So like then R could just be A0, A1, E1, and maybe that's it. Maybe that's all I want. That's a relation. So we can't call it a function because if we're thinking of the sort of left coordinate as the input and the y coordinate, or sorry, and the right coordinate as the output, A would have 2 outputs. So, we can also, so we can illustrate as well. Whoa. So, something like, we have A here and it goes to 0 and 1, and then we also have B, which just goes to 1. So we can like draw or visualize a relation like this. And you can just kind of see here, like this kind of makes it not a function, because if I said for each input there's 1 output, well, my A and B are my inputs, but A would have 2 outputs, so it's not a function because each input needs exactly 1 output. So not a function, but still a relation because it's just a subset of the Cartesian product. So you can take any other subset and that would be a different relation. Another relation that we could just kind of, just to give you sort of a wide range of examples. So if A is the set of natural numbers, right? Remember, that's just 0, 1, 2, etc. And B is a species of animals. Then the relation, put it over here, is going to be all ordered pairs such that n just has to be a natural number. So we'll take all of A basically and cross it with, so each n will be associated with, will be like the number of legs that animal has. So such that n is, oops. And, species A has n legs. Okay, so that's kind of silly, but hopefully it'll illustrate a nice point. Well, maybe we won't take all the natural numbers, yeah. But anyway, that's okay. So, what are some ordered pairs in this set? So some elements of R would be, 0, snake. Snakes have 0 legs. Snakes are animals. I guess maybe that's, I should maybe species. I'm not a biologist here. Species is probably the wrong word because I know there are different species of snakes. So just bear with me. Sorry for all you biologists out there. Also worms. So 0 worm, and there's more animals with 0 legs. Fish. What about 1? I don't know that there are any animals with 1 leg. Maybe someone correct me if I'm wrong. But so then we would never have any ordered pair that starts with a 1. Uh, and then 2, lots of 2-legged animals, right? People. What am I saying? Sapien. 2, chicken, lots of ordered pairs. There are lots of four-legged animals, et cetera, right? So the list goes on. And you can, you can visualize this relation as well, right? Like 0, snake, worm, and there are more. So, there'd be more arrows just coming off of 0. So this is a relation as well. Right? They can get, as crazy as you want. Okay. So I want to do one more example that's actually an algebraic function. And we're going to see kind of how it's also a relation, like what I was saying before, where the Cartesian product, or sorry, the XY plane is just the Cartesian product of real numbers and real numbers. So we can just use that to our advantage. So f of x, well, maybe, yeah. So f of x equals x squared. That's the rule. And then I'll say the domain and codomain are both R. Okay. So what does this function look like? Well, that's the domain and codomain. The domain is, what's the x value, and the codomain could be any of the y values, right? So that kind of illustrates all of it. And then the actual point in the set, so these are all of the elements in the relation. In other words, ordered pairs. Right, and seeing it as a table might be helpful too, right? So like, there, so f of 2, that's 4. And so what's the ordered pair? Just 2 comma 4, and that's a point on the parabola. I should have made this in orange. Not that it's a big deal, but just imagine. F of -1 equals 1, so that corresponds to the ordered pair -1, 1. F of 0.5, oops, 0.25, so that's, this ordered pair. And of course, there are infinitely many with this domain and codomain. And so this is a relation because it's just a subset of R cross R, right? It's the orange subset. It's the parabola, but this is a subset of the whole plane. And so it is a relation, but it's also a function, right? Because for each input, there's exactly one output. Never going to square something and get 2 possible answers. Square rooting is a different story, but yeah. So so what I'm trying to say is that every function is a relation, right? Where you just think like input, output, and all of those pairs. But not every relation is a function. Right, and so to connect this back to sets, right, or just to kind of keep you remembering what we've been doing and making these connections, we can do a Venn diagram to illustrate this. The set of functions is a subset of the set of all relations. Right, and so this is a Venn diagram. And so the set of all functions is a subset of the set of all relations. Okay. All right, that's it for this video. There will be one question here at the end. Yeah, see you in the next video.